You ever wonder how some modern medicines can be so incredibly precise? I mean, targeting just the cancer cells and leaving the healthy ones alone? Well, a lot of the time, the answer is a wild class of drugs that are basically the immune system's own hired guns. All right, so let's dive into the world of monoclonal antibodies. And just so we're clear, this isn't some small niche corner of the pharmacy. Monoclonal antibodies, or MMOBs for short, are the single largest class of biologic drugs on the entire planet. We're talking drugs that come from living cells, not just chemicals mixed in a lab. And they're used for pretty much everything, from cancer to arthritis to migraines. So, what are they, really? Well, that brings us right to the antibody revolution. The big idea here is taking the blueprint of our body's own natural defenders and engineering them, fine-tuning them into these hyper-specific, super powerful weapons against all kinds of diseases.
Okay, here's the core concept. A monoclonal antibody is an army of identical clones. Every single molecule is a perfect copy, and it's programmed to hunt down and lock onto one and only one specific target. You can think of that target, scientists call it an antigen, as a unique little flag sticking off the surface of a cancer cell or a virus. But to really get how they work, you've got to look at how they're built. So let's get into the anatomy of an MAB and break down this absolutely brilliant blueprint. What's so cool is that scientists didn't have to invent this thing from scratch. This classic Y shape you see here, that's straight out of nature's playbook. It's the blueprint for a natural IgG antibody, which is the most common kind floating around in our blood right now. The two arms at the top, that's the business end. That's what grabs the target. The stem at the bottom is called the FC fragment, and believe me, it's just as important. So you can really think of this thing as two different machines welded together. The top part, the Fab, is all about targeting. It decides what the antibody latches onto. But the bottom part, the FC, that's the action module. It determines what happens next after it's grabbed on. Here's the perfect way to picture it. The Fab is like a super precise GPS coordinate that says the enemy is right here. The FC, on the other hand, is the radio that calls in an airstrike from the rest of the immune system to come in and wipe that target out. Two totally different jobs all in one elegant molecule. Okay, so we've designed our perfect little smart bomb. But what happens once you actually put it inside a person? Well, for a huge molecule like an MAB, the journey is completely different from just swallowing a pill. I mean, just look at this comparison. A MAB is a giant. It's about 150 times bigger than a small molecule drug like aspirin. And because it's a protein, if you tried to swallow it, your stomach would just digest it like a piece of steak. It's why you can't take them as a pill. They have to be given through an IV or an injection. But here is the incredible payoff for being so big and complex. Get this, 21 days. That is the typical half-life for one of these antibodies inside your body. Now, to put that into perspective, most other proteins in your blood are gone in a matter of hours. This is just on another level. Which, leads to the big question. If our body is constantly recycling old proteins, how on earth do these things manage to stick around for weeks at a time? The secret is this absolutely ingenious recycling system called the FcRn salvage pathway. What happens is, when a cell swallows an antibody to destroy it, the antibody grabs onto this special receptor inside called FcRn. This receptor is basically an escape hatch. It escorts the antibody right back to the cell surface and just spits it out, unharmed, back into the blood. It's a biological get-out-of-jail-free card. But there's always a but, right? There's a catch. For all their cleverness, sometimes these drugs can actually trigger the very system they're supposed to be helping. And this brings us to the huge challenge of immunogenicity, which is just a fancy way of saying what happens when your body fights back against its own medicine. So here's the problem. A patient's immune system can look at this incredible, life-saving drug and go, "Whoa, hold on, I don't recognize you." And then it does exactly what it's designed to do. It starts making its own antibodies to attack the drug. We call these anti-drug antibodies, or ADAs. And not all these ADAs are created equal. You've got your binding antibodies, which just kind of swarm the drug and get it cleared from the body faster. Not great, but manageable. The real troublemakers, though, are the neutralizing antibodies, or NAbs. These are way more serious. They bind directly to the drug's targeting system, the Fab part, and physically block it from doing its job. They make the drug completely useless. And this has massive real-world consequences. A patient might be on a drug like infliximab, and it works like a miracle for 6 months. Then all of a sudden, their symptoms come roaring back.
It's not because the disease got worse. It's because their own body has built up these neutralizing antibodies, turning their life-changing medicine into, well, very expensive water.
So when you put it all together, the elegant design, that long journey in the body, and even the challenge of the body fighting back, monoclonal antibodies are really a new frontier in medicine. We've learned how to hire our immune system's best soldiers. And that leaves us with a pretty exciting question. With this technology getting better all the time, what disease will they conquer next?